Hello and welcome to another podcast. This one is going to be on alkanes and alkenes, and we're talking absolutely entry level. I'll assume a certain amount of nomenclature knowledge, but other than that, we're going from ground zero in this. And one just look at what the difference is initially, and then we'll go into like some nomenclature formula differences and so forth. But the definition of an alkane is a hydrocarbon that contains just carbon and hydrogen, hence the name, and all the bonds are single bonds. Everything's a sigma bond within a alkane, as opposed to an alkene, which has again carbon and hydrogen. It's still a hydrocarbon, but it has a double bond. So it has a sigma and pi between a couple of the carbons. Could be one pi bond, could be multiple pi bonds, and specifically, I should say a double bond. So it contains just one pi bond between a carbon and carbon somewhere in the structure. So I want to start formula wise and introduce terminology known as aliphatic. Now, we often use the word saturated. Saturated means no pi bonds. So a saturated fat is completely sigma bonds. They're flexible. They can pack together more tightly. We learned that in an earlier chapter when we looked at melting points. This time, I want to talk about aliphatic, meaning it has no units of unsaturation. So what that means is the maximum number of hydrogens are in the carbon. So looking at these formulas, if I have one carbon, the maximum number of H's can have is 4 because it makes 4 bonds. If I have two carbons, like C2H6, then each carbon is making a bond to another carbon, so it only has 3 more bonds to go to hydrogen. So the maximum it can have is 6, 3 per carbon. If I go to 3 carbons, again, they're each making bonds to carbon. The end one, this terminal one and this terminal one, still have room for 3 more H's. When the middle one has 2 bonds of carbon, so it only has a max of 2. So if I just sort of look at this and say that the terminal one is always going to be a CH3, terminal one's always CH3. That means the formula for an alkane can be summarized as H3C at one end, connected to a carbon in the middle, connected to its CH3 at the other end. The middle one has to be CH2 and whatever number it is. I'll just put a random number mark here. Meaning it could be CH3, CH2, CH3, like case of propane. It could be CH3, CH2, CH2, CH3, like butane, or CH3, CH2, 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 CH3, etc., like pentane. And so we always end up with a CH2, CH3, CH3. So we're always going to have some multiple of CH2 plus an extra H on the end, extra H on the end. So I'm actually going to change my drawing to come up with a cool little shortcut formula. And that is you have an H on one end connected to a whole bunch of CH2s connected to an H, meaning the terminal end has a CH3, CH3. So let's just count these as separate. And I have a group of CH2s in the middle. I have H on the end, group of 2, 2 H's on the end, and 1 CH2. So every single alkane is going to fit this formula, meaning it will have however many carbons will be N, and the hydrogens will be 2N plus 2 extra at the end. Hence, we come up with this formula, CnH2n plus 2. So an aliphatic alkane, meaning no rings and no pi bonds, completely saturated, will have this formula, H, CH2 grouped N and H, or C, N, H2N plus 2. Okay, so that's where we're going to come from. So something called saturation and aliphatic saturation, 2 things we're going to consider. I also want to consider then non-cyclic alkenes. So non-cyclic alkenes, if I take any chain length. So let's take the C4H10 that I didn't draw. So C4H10 has 1, 2, 3, 4, 5, 6, 7, 8, plus the 2 H's that dangle off the end. So C4H10. But if I were to form an alkene, I'd have a double bond. Let's say I'm just going to pick this arbitrary middle one. I now have too many bonds of carbon, so I would have to get rid of this H and get rid of this H, which would now take me from what was originally C4H10 down to now C4H8 when I had a double bond in there. So an alkene, a double bond, is what's known as unsaturated, and unsaturated because it does not have the maximum number of H's. So as I mentioned, possibly in earlier podcast or maybe in lecture, you always want to add the word with hydrogens after somebody says saturated. So these aliphatic alkanes are saturated with hydrogens. The maximum number of hydrogens are on there. These non-cyclic alkenes having a double bond are not saturated with hydrogen because you have to lose two H's to make a double bond from the maximum number. So we have a cool little shortcut. So if you give me a formula, let's say you tell me C6H10. Well, I know the maximum for 12 would, or for 6, excuse me, would be 12 H's plus 2 for the N, so 14. If it's 10, that means I'm short 4 H's, hydrogen deficiency of 4. So I could have either 2 pi bonds or a ring and a pi bond or 2 rings. And so we'll get more into rings in a second here, but if it's linear, if there's no rings, then I know that I have 2 pi bonds because I'm short. Maximum number of hydrogens on C6 would be 14. So if I have 10, I'm short 4. Okay, so far so good. So what I want to do is I want to then click on, I'm going to get rid of what I've written and emphasize a few things here. So number one, let me erase what's in the way and say that every pi bond molecule results in 2 less H's in the structure. Pi bond is considered a unit of unsaturation. Okay, so far so good. Now I want to consider rings. So one type of unit of saturation is mentioned is the pi bond. These have 2 less H's because they have a pi bond, and mentioned rings can also have the same situation. So I'm going to start this time with its grouping, but I pick 3 because you can't make a ring with 1 carbon, can't make a ring with 2 carbons. You need at least 3 carbons to make a ring. So C3H8 is 2N plus 2. So that one's saturated. C4H10, 2 times 4 is 8, plus 2 more is 10. That's saturated and aliphatic linear. C5, so 2 times 5 is 10, plus 2 is 12. That one's same story. Now let's consider what happens if I want to make a ring. So I'm going to draw this a little bit different. So I'm going to draw 5 carbons. I'm going to draw 1, 2, 3, 4, 5 carbons. Every carbon has 2 H's. Sorry for the very large H, but that's a product of where my template is. And then we also have the 2 N carbons have a dangling H's. So to make a ring, what I need to do is I need to get rid of the H's. I'm going to choose the dangling H's because they're colorized for me. I'm going to cross those out and make a carbon-carbon bond. So that would mean I have a carbon, 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 and then 1 more carbon bond. So there's 5 in a ring. Each carbon in that ring has 2 H's, so 2, 4, 6, 8, 10. So if I want to make a ring, I have to get rid of 2 H's again, just like I did to make a pi bond. So I'm going to erase this because that's right in the way of where everything's going to come up. So notice if they have monocyclic, 1 ring, they have 1 less pair of H's. So just like you lose 2 H's for a pi bond, you also lose 2 H's for a ring. So same story here, except the unit of saturation is the ring. So for every ring in a molecule, will result in 2 less H's atoms in the structure. Okay, so for instance, let's go back to that C6H10 that I tossed up there. 14 max H's would be true. Only have 10. Therefore, 4. Those are different. 2 H's per unit of saturation. So we're going to take 4 divided by 2 equals 2 units of unsaturation. Now, you're going to see me use different words throughout this lecture and just from this point on. You'll hear me use sometimes degrees of unsaturation, units of unsaturation, or hydrogen deficiency number. They're all saying essentially the same thing. We calculate slightly differently, but come with the same number. So if you have a deficiency of 4 hydrogens, that means you have 2 units or 2 degrees of unsaturation. I'm using all the terms interchangeably. I don't care which one you lock into, they're all saying the same thing. So that would mean this structure would have to have 2 pi bonds, again, a ring and a pi bond, or 2 rings. So we could draw it. I'll draw a 6-member ring for ease and put a double bond in it. I would have 1H, 2H, 3, 4, 5, 6, 7, 8, 9, 10 H's. Perfect. Or I could have 2 pi bonds. Let's make sure I have the right number of carbons. 1, 2, 3, 4, 5, 6. Perfect. And I have 1, 2, 3 H's, 4, 5, 6, 7, 8, 9, 10 H's. I'm not going to draw the H's in this time. But I have a ring and a pi bond. I have 2 pi bonds. That 2 pi bond could also be a triple bond. And last but not least, I could have 2 rings. That's going to be really tricky to do, but I'll draw it in a, what ultimately we'll realize is very unstable, but 2 rings. So 1, 2, 3, 4 carbons and a 5th and 6th carbon. So 2 rings with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 H's. Okay, so this is one of those things, it might seem weird at first, but it's bookkeeping and how this becomes applicable. If I tell you the formula for an organic compound, you can, in your mind, decide, okay, how many pi bonds are possible, how many rings are possible, therefore, what type of functional groups could be possible. And that's ultimately where we're going to go with it. So, want to take a side note because I kept on dropping names. So just to make sure we remember the name thing, this is going to hopefully go through pretty quick. It's as simple as counting in OChem speak. So 1 carbon, 2 carbon, 3 carbon, and so forth. So here are our saturated aliphatic alkanes: 1 carbon, 2 carbons, 3 carbons, 4, 5, 6, etc. You count meth, eth, pro, bute, pent, hex, hept, oct, none, and dec. That's 1 through 10. I fully expect you to know 1 through 10 routinely. And I will occasionally toss in a 12 like dodeca, not because I think it's really important, but because you're going to learn in OChem when you get to something called electrophoresis. For proteins, you'll toss in sodium dodecyl sulfate. As you need to know, dodecyl is 12 carbons. So it's not that it's really useful in OChem per se, any more useful than any other number. Excuse me, it has biorelevance. Okay. You also need to know functional groups. We did groups, so you've done some nomenclature videos at this point, so hopefully you're up to speed, but alcohols have the same lead-in, meth. You have the and, but instead of ending in E, they end in all. So methane all, ethane all, propane all, butane all, which you drop the E, becomes methanol, ethanol, propanol, butanol, and so forth. So 2 carbons, so ethanol, 1, 2, 3 carbons, so propanol, 1, 2, 3, 4 carbons, so butanol. Okay. Carboxylic acids, we'll toss those in there as well. Same rules. 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6, 7, 8 carbons. So 4 carbons would be butanoic acid. 6 carbons would be hexanoic acid. 8 carbons would be octanoic acid. So hopefully these nomenclature rules are reasonable. When we start adding branching, that's where it gets a little funky and complicated and the rules bog down. But the straight chain, hopefully, nice and easy. And you should be so happy you just cheer, F, Butte, Hex, oh, gotta say, names rock, yay. Okay, if you ever do that in public, you will be shamed, but you'll lose all your friends and have more study time. Okay, onward we go. So drawing linear alkanes. So the shorthand, again, points represent carbons, terminating point or intersection point. So 1 carbon, 2 carbon, 3 carbons, 4. There's also 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 H's not drawn in. So drawing linear alkanes, key thing, this formula isn't just for the straight chain one, but it's also going to be for ones that have branching. Well, let's just get the straight chains down pat. So 4 carbons, 1, 2, 3, 4, 5 carbons, C5H12. 6 carbons, 1, 2, 3, 4, 5, 6, check. And if I really want to, as much as 8 carbons. So 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons. And then because I see no rings and no pi bonds, I need to know automatically 2 times 4 is 8 plus 2 more 10, so there's 10 H's. 2 times 5 is 10 plus 2 more 12. 2 times 6 is 12 plus 2 more 14. 2 times 8, 16 plus 2 more 18. So in other words, I know how many H's are here without doing any counting because I know there's no pi bond and no ring. So it's got to be fully saturated and aliphatic. Okay, as mentioned, so I'm just going to put the name for this. This is butane. And if you want to add an N-butane to stand for normal butane, you can, but I'm just going to go with butane. But you can also have C4H10 where you have 1, 2, 3 carbons and a methyl on the side. So just to double check, I would have 1, 2, 3 H's, 4, 5, 6 H's, 7, 8, 9 H's, 10 H's. So it still works. It's just not a perfectly linear one. So linear alkane here, but if I want to, I have this one, which this is known as, I'm going to just number 1, 2, 3, nomenclature rules. So 2-methyl propane, meaning the longest chain is actually only 3 carbons. 1, 2, 3. So it's a propane and has a methyl group, an extra carbon off the side. Can't really do much beyond that. So I can't really make it 2 carbons long and then add substituents because the substituent makes it longer. So there's something we're going to do shortly, and that is for a given formula, try to figure out the maximum number of isomers you can have. So this is C4H10 butane. This is also C4H10 2-methylpropane. These are known as structural isomers. So I should write that up here. These are structural isomers, meaning same formula, different connectivity. And because of that, we say they have different structures, different backbone structures. So structural isomers, hopefully this seems reasonable. So the way we do it is this. 5 carbons is the longest possible chain. There's only one long chain one. But if I shorten the chain from 1, 2, 3, 4, 5 to 1, 2, 3, 4, then I can have a methyl just like I did up here. So this is pentane. This is 2-methyl butane. And why do I choose 2 and not 3? Rule preference. So I'm going to number 1, 2, 3, 4, as opposed to going 1, 2, 3, 4. You always want to put the substituent on the lowest possible number. So this group here, this substituent, the thing that's not part of the longest chain, dictated the number. So I could either count left to right and make it on number 2, or right to left and make it on number 3. We choose number 2. So if I were to draw it like this, I'm going to try to draw what I think is a different one. 4-carbon chain, longest chain minus 1. Now I'm going to put this on 3. So I'm going to call this 1, 2, 3, 4. So 3-methyl butane. And I find out I've numbered it wrong because this thing always has to be on the lowest substituent. We actually now number from the other direction. 1, 2, 3, 4. So that's not actually an isomer. That's the exact same compound, but spun around. So I basically took this molecule and rotated it by 180 degrees. So this went over here. This group is now down over here. 4 now comes up and is over here. So I didn't draw anything unique. So these are the same molecule. They're both 2-methylbutane. So that's going to be a cool little shortcut if you're trying to figure out whether you have the same compound or whether you have 2 different compounds. Try naming them. If they both have the same IUPAC name, you have the same compound. Okay, let me get rid of all this and tell you there's one more thing we can do. We can we tried all the four possibilities, and there really is only one. But there's also a three possibility. So 1, 2, 3 carbons. Now I have two groups, you know, methyl and methyl. So this one, whereas this is pentane, this is 2-methyl. Butane. This is now propane because the longest chain is now 1, 2, 3 carbons. But this is 2,2-dimethyl. Barely fit that in. So sorry, I can't read it, and I'm right next to it, so it's got to make it bad for you. But it is 2,2-dimethyl propane. These are all considered isomers, meaning they have the exact same formula, C5H12, but they're connected different. Chain of 5, chain of 4 with 1 coming off, chain of 3 with 2 coming off, a middle carbon. Okay, so I'm going to get rid of my drawing and let the next one come in. Now I'm going to totally regret this. So as I mentioned before, this one doesn't count because it is the same one, 4 carbons, and this is now carbon number 2. That one's out, but this one is fair game. So this is where I'm not going to name them, but you should probably sit there and name these again. Name what this one is, what this one is, and what this one is. And note that they have 3 different IUPAC names. So there are 3 unique structural isomers of this formula. When we start getting to C6, it gets a little more complicated, but we're going to follow the same pattern. Longest chain, straight chain was 6, which means I can have a 5. But on that 5, I now have some choices because I now have carbon 1, 2, 3, 4, and 5. 1 is the same as 5, if you will. 2 is the same as 4. 3 is in the middle. So if I were to take this and try to draw it over here, if I did this, this would be just the exact same compound. It would still be 1, 2, 3, 4, 5. And so it would still be 2-methyl pentane, 2-methyl pentane. Okay, so that didn't help, but what does help is I have that middle spot that's going to be a little bit different. So this case here, this first one is 2-methyl pentane. This is 3-methyl pentane, which means different IUPAC name, they are unique. I exhausted all of the 5-member rings, so 5-member chains, excuse me. I have a 6 carbon chain, 5 carbon chains with 1 coming off on the, can't be on the end because that would just make a longest chain. So I go 1 in, I put it there, and I move to the middle. Middle's going to be different, but if I move out to the end, it's the same thing. Now I can put 4 together. So 4, 1, 2, 3, 4 in a chain. This is 2,3-dimethyl. I could also put, sorry, one more for this one. Let me squeeze this in. I could have also put 2,2-dimethyl butane and 2,3-dimethyl butane. So there is 1, 2, 3, 4, 5 possibilities. This one there were 3, this one there were 2. There's no easy systematic way, like a formula to get it. You just have to be very organized, systematic. So if you're asked how many isomers, take this number, make a longest chain. There's always a longest chain. Then make a 5 and put it in different spots. Make a 4, make different spots. Can't go any lower than 4. Once you cut it in half, you can't have that short of a chain. So C8H18, I would draw the 8 carbon one. I draw a 7 and put it on 2, 3, and 4. I draw a 6 and put it 2, 2, 2, 3, 2, 4, 2, 5. And then I do 3, 3. And then I do 3, 4, 3, 5, 3, 6. And then I do 4, 4. And then I do 4, 5. So you get a certain rhythm to these things. You start figuring out how this goes. And then I would do finally this one, 5 carbon chain, where I've done 2, 3, 4. But I could have 2, 2, 3, 2, 2, 4. I could have 3, 3, 2. Nope, 3, 3, 2. Nope, I already had one of those. So I can't have both. I can have one or the other. But you can start systematically putting them on. This will be a homework question that you'll run into, maybe a quiz question, I don't know. But hopefully this seems okay. You're drawing linear alkanes. Okay, so far we've just played more game than anything else. Want to add one more piece to it, and this becomes, I think, the most important part of doing all of this. And that is identifying uniquely as we move these things around. So some of the structures I just drew, here's octane that we just did before. So 1, 2, 3, 4, 5, 6, 7, 8. I did 2, 3, 4. This one is 2, 3, 3, so slightly different. But you now have different amounts of carbons on there. So when it's a straight chain, your two dangling ones, the CH3s, are what's known as primary. They're carbons that have only one other carbon attached. And the middle ones, the CH2, the methylene carbons, have two other carbons attached, so we call them secondary. So this yellow is dangling off, this yellow dangling off. You have 1, 2, 3, 4, 5 dangling off. So yellow is known as a primary carbon. The methyl groups dangling off the end are primary, meaning they are only attached to one other carbon. One bonded carbon, one bonded carbon, and so forth. The brown ones have two other bonds of carbon, so we call them secondary carbons. You can kind of follow the pattern here. The pink one is connected to 1, 2, 3 other carbons, so we refer to it as a tertiary carbon. And finally, this green one is connected to 1, 2, 3, 4 quaternary carbons. How this becomes important is if we know how many carbons on there, then we can deduce how many non-carbons, be it hydrogen or some other substituent. And so if I have a primary alkyl halide, that means I have it on one of the yellow carbons, whatever the halogen is. If I have a secondary alcohol, I have it on one of the brown carbons. So instead of being so specific about 2-octanol, 3-octanol, 4-octanol, instead I'm just going to say secondary alcohol. It's on one of the interior ones. If I have this one and I call it a tertiary alcohol, that means the OH has to be on the pink one. And if I say quaternary alcohol, I'm going to lose points because it already has 4 bonds, can't have it. So you can have a primary, secondary, and tertiary alcohol, can't have a quaternary anything because carbon has already reached its Honk limitations. It's already reached its maximum of 4 bonds to carbon. Okay, so this becomes really key. You're going to hear me say this a lot in class from this point on. Primary, secondary, tertiary carbons. And we're going to eventually extend it to other atoms as well. But for now, let's just focus on carbon. Okay, so I just hit what is the end of this. So have an absolutely wonderful day. Sorry that that screen popped up, but now you know roughly where we are schedule-wise. But there's your alkenes. Thank you, and have a wonderful day. Bye.